Okay, we've been through chapter 4, been going over chapter 4. We've been all the way up through section 6. You've already done the progress check. Let's continue and try to get the last part of this chapter down. All right, so we're going to talk about skin. We're talking about the integumentary system, and we're going to list some of the functions. One would be heating and cooling, another would be protection, another would be preventing you from evaporating, stuff like that. We'll go over this. Anyway, you're going to compare the structure and the function of the epidermis and the dermis. The epidermis means, epi means above, so above the dermis. This is the outermost layer of the skin. This is where you have all that stratified squamous that is abrasion resistant that we were talking about before. And then accessory organs for the skin, things that they do. We're talking about things like sebaceous glands that help keep the skin waterproof, or sweat glands that help with evaporation and cooling. Anyway, we'll get to it. So, learning outcomes. We summarize the function of each organ in the human body. Organ system. Sorry, we're doing organ systems. We're going to talk about what the different organ systems do. We'll talk about the cavities and the different names of membranes in the body. The big ones we're probably talking about here would be in the thorax, the area above the diaphragm. We're going to be divided into 3 parts: a left pleural, a right pleural, and in between them, mediastinum or mediastinum. Those are defined by the pleural membranes, the membranes around the lungs. They actually form a wall separating the right side, the middle, and the left side. So left lung and left pleural cavity, right lung and right pleural cavity, and the heart in the mediastinum. All right. The main membrane that we deal with in the abdomen is going to be the peritoneal membrane. Anyway, but we'll get to it. We'll get to it. So this is what we're going to do. An organ is a group of tissues that have a common function. Groups of organs that work together have a similar function or organ system. So it says some of these systems, like the respiratory system, occupy specific cavities. So respiratory system, we're talking about things like the trachea and the bronchi, the lungs and the diaphragm. Okay. And it says others, like the muscular system, are found throughout the body. Yeah, absolutely, definitely true. Another one that would be like that would be the nervous system. Anyway, organs with cavities are lined with membranes. We'll give names, many which secrete fluid. The membranes that make fluid, that fluid is called serous fluid, serous. And that serous fluid, what you'll have is a membrane, a very thin layer of serous fluid, a couple molecules thick, and another membrane. And that serous fluid, that's lubrication. Just like when your piston goes up and down inside the cylinder, there's oil to keep it from rubbing on the side. That lubrication makes it easier to move. Well, the same thing when you have 2 layers. Say we take one of those membranes around the lungs, the pleura. We have the visceral. The V in visceral should remind you it is very close, like it's stuck to or part of the organ. So we have the visceral pleura, and then we have the pleura that's to the periphery, to the outside of the body. That's parietal pleura. So there are your mnemonics. V for very close when you're talking about visceral pleura. That's actually stuck to the organ, part of the organ usually. The P for parietal, that reminds you that layer is on the periphery, it's away from the organ. But between those two, you have very thin layers of serous fluid, and that fluid lubricates. It allows, like when the lung expands and pushes on the chest cavity, or the lung contracts and moves away, you don't have that rubbing cause pain. normally. In fact, if you get inflammation of the pleura and they're not moving well because you don't have the fluid, that could cause a condition like pleurisy. Okay, problem with the pleura, hurts to breathe. All right, so anyway, we've got that. We got this about serous fluid. The book has a pretty chart here with functions of the integumentary system, cardiovascular system, lymphatic and immune, digestive, respiratory, urinary. I'm going to check and see if it's on the next page, but I don't see the nervous system or the endocrine system in there. I want you to know it's real important. They work in different ways. Their effects last different amounts of time, but the nervous system and the endocrine system both are super important for allowing the different organs to integrate, to work with one another. For instance, you can have this organ send a signal to that organ saying, hey, something's happening, get ready. Anyhow, let's move on. Yeah, okay, so we have two slides here that list functions of the immune system. The first slide has integumentary, cardiovascular, lymphatic, digestive, respiratory, and urinary systems. The second one has skeletal, muscular, nervous, endocrine, and reproductive systems. Know those things. I will certainly, trying to think the best way to word this. Short version is those are testable questions, and I'm certain that there will be a couple questions derived from them. Anyway, moving on. So we've got two main body cavities: ventral, which is closer to the front of the body, and dorsal, which is closer to your back. Anyway, the ventral cavity is the thoracic, the abdominal, and the pelvic. I want you to remember that abdominopelvic is one space, one cavity, but there's an abdominal region and a pelvic region. So those are kind of like, you imagine which is which. The thorax and the abdominopelvic, on the other hand, that's a serious difference. That's a difference because you've got a wall made out of the diaphragm muscle. Anyway, the dorsal cavity, you have the cranial, that'd be the head, and the vertebral canal. And it's also important to know that not all the organs are in one of these, not all the organs are in one of these cavities. Your kidneys are retroperitoneal. That means they are behind the peritoneal cavity. The peritoneal cavity is another name for the abdominopelvic because the abdominopelvic are lined in a membrane called the peritoneum. Anyway, the kidneys are behind that. They're embedded in the body wall. All right, so let's move on. Pretty picture explaining the things that were said on the last page. What it adds in addition is what organs are in those spaces. For instance, the thoracic cavity has the lungs and the heart and the bronchi. We've talked about that before. All right, so definitely know that. Hold on. Life is better with Mountain Dew. Okay. You can see that the pleural space contains the lungs. The pericardial space, that's also the one that I was calling the mediastinum. It's another name for it. The pericardial space has the pericardial membrane. You will see, and that's where the heart is. That's also where the brachii and the esophagus go through. Bronchi and esophagus, trachea, all that stuff. When you look at this drawing, if you look at the lung right here, and we have the pleura, this is parietal pleura. Here we have epicardium. The dividing, the division, the wall between the pericardial space, the mediastinum, and the pleura is made up out of a membrane from this side touching a membrane from the other side. So say you have a lung over here and you've got pleura. Here you've got pericardium. Okay, the two membranes together form the wall. This would be the wall that separates this body cavity over here, pleural space, from this body cavity in the middle of the chest, which would be the pericardium or the mediastinum. All right, moving on. And again, like we said before, there is between the thoracic cavity at the top and the abdominopelvic cavity at the bottom, there's a nice solid dividing line with the diaphragm. You don't have a division like that between the abdomen and the pelvis. That's more imaginary based on region. All right, so let's move on. The body membranes, lining cavities, and internal spaces of organs and tubes that open to the outside. All right, so types of membranes. You have mucous membranes. You might guess they make mucus. Example of that would be the ones in your nasal passages. Serous membranes, the one I just described that you have, say, between the two layers, the visceral and parietal, on the pleura, or the visceral and parietal on the pericardium. Those are the ones, serous membranes are the ones I described, that have serous fluid that lubricates the movement, makes it easier to move, makes it less painful. Synovial membranes, those are ones we find in joints. They keep fluid inside the joint capsule. And meninges are the ones around the brain. We're talking about things like the dura intima, the intimate layer of the pia mater, and the arachnoid layer, and the dura mater. Dura mater, outermost of the brain's coverings, durable, thick, empty bag. In the middle, you have the arachnoid matter, really thin membrane, very porous. Think of it like a spider web. That's why arachnoid. And then the one in intimate contact with the brain actually touches the brain, and every groove or wiggle it's lined, the membrane follows that. That one is in intimate contact with the brain. That's the meninges that we call the dura intima. All right, moving on. So mucous membranes line tubes in the digestive system, respiratory system, urinary system. There's epithelium and loose fibrous connective tissue. It has goblet cells that make mucus. That's worth knowing. Goblet cells make mucus. All right. They line cavities that aren't open to the environment. They cover the surface of organs. Yeah. Here we have serous membrane, the pleura, and it covers the lung. The pericardia, it covers the heart. And the peritoneum covers things like the intestines and the abdomen. All right. Synovial, we already said this is in the joints. They make synovial fluid, which is lubrication for the joints. The meninges, they're only connective tissue. They are around the brain and spinal cord. And I already told you we've got three layers there in the brain. The dura mater, arachnoid mater, and pia mater, from outside to in. Anyway, meninges are, well, meningitis is inflammation of the meninges, inflammation of these membranes around the brain and spinal cord. All right, here's another one of those check your progresses. I'm going to pause. You can check. You pause this video, see if you can answer the questions. If not, go back and watch again. Um, Once you can answer the questions in this check, we'll continue on. Oh, hey, here we go. All right, so let's talk about homeostasis. Homeostasis is maintaining constant body conditions inside. All right. Homeostasis is why we say, oh, well, you have a temperature. Oh, you don't. There is a normal temperature, 37 degrees Celsius, that the human body is supposed to be at. And maintaining that would be homeostasis. The goal is to have constant internal body conditions. Now, you can do that with feedback mechanisms. There are positive and negative feedback loops. Homeostasis tends to be a negative feedback loop. Most examples are negative feedback. Let's say your body temperature is supposed to be here at 37 degrees, and you get a little hot. You're higher than that level. So your body says, hey, let's sweat so we can cool off. Well, then you may go down and the temperature may be too low, and your body will say, hey, stop the sweat. Hey, maybe even shiver some, and then you'll drive it in the other direction. My point is there's a constant level you should be at, and you might be a little higher than that some of the time, a little lower than that some of the time, but you're always around it. You're always approximating it. And the negative in the name, negative feedback, is, oh, I'm overheating. Let's change. Let's sweat. And as you do, the temperature that was too high is going to go down, 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 down. Eventually, your body will say, wait, stop that. That's enough. Go in the other direction. That negative in the name negative feedback is that you do something and then you got to stop it. Don't. Positive feedback mechanisms are a lot more rare. I can only think of two off the top of my head. One is oxytocin causing uterine contractions to deliver a baby. And the other one would be blood clotting. And so let's go with the first one I mentioned, that's easier. A positive feedback mechanism would be we have a little bit of oxytocin, or synthetic in the hospital. We have a little bit of Pitocin. It causes uterine contractions. And those uterine contractions cause more oxytocin to be released, causes stronger contractions, which causes more oxytocin to be released, which causes even stronger contractions. It's positive. You're building on it. And you go, 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 get stronger, 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 stronger until the baby is pushed out. Same thing with the circulatory and blood clotting. Blood clotting is a positive feedback mechanism, and you go through step after step after step, causing a cascade, and you get more clotting, which causes more chemicals that will cause more clotting, which causes more chemicals that will cause more clotting. And you do that until you've stopped bleeding. Um, Positive mechanisms tend to excite, tend to make the effects that they're causing get more extreme, more extreme, more extreme. Negative, you do a little of this, oh, that's enough, go the other way, go down. Oh, no, 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 done. So you go up and then down and then up and then down, and you're wavering around this steady state, this homeostasis you're trying to maintain. All right. So homeostasis, constant internal conditions. The examples of blood is the book is using are blood glucose, body pH, body temperature. Temperature is the example we used. If conditions vary too much, you get sick. But I do want to point out it could be a little different than they're saying. Um, your body might change from the normal because you are already sick too. It's true that if your fever goes too high, illness can result. But it's also true that the reason you probably have a fever is your body is trying to raise the temperature to make it hard for a bacteria to reproduce inside of you. Your body's trying to hold the bacteria at bay so the white blood cells can do the job and go in and kill them all before you have more and more and more bacteria. So anyway, what I'm getting at there is just to let you know that we have an internal body condition. We try to stay there. The book is right. When we're not there, when things are off, it's probably a problem. That's true. The only exception I have to what the book said is which is cause and which is effect. Is illness because the temperature is too high? Could be, but it could also be the other way. Temperature is high because you're ill and you're trying to fight. It's just that if it goes too high, then you have a whole host of other problems. Anyway, moving on. So the internal environment, we've got blood and interstitial fluid. The book should actually say blood, lymph, and interstitial fluid. But I think I've mentioned before to you guys that lymph drains the extra like fluid from blood goes into the interstitial fluid. Most of it goes back into the blood, removing waste from the cells. Some of it stays. You don't want the buildup, so you have the lymphatic system that drains the extra interstitial fluid away, and then it sends the interstitial fluid through the lymph vessels back into the circulatory system. So in reality, where the book is saying, oh, there are two parts, kind of, but you could call it three. And more importantly, they're all kind of one, because you have individual molecules of fluid that will be, I'm part of this. No, I'm part of this now. Oh, I'm part of this. Anyway. So blood delivers oxygen and nutrients to tissues, carries away carbon dioxide and waste. Yeah, we got that. Interstitial fluid surrounds the cells. Substances are exchanged through it. What substances? Well, things like the carbon dioxide and waste are exchanged for oxygen and nutrients. That's how cells get the things they need and get rid of the things they don't want. It's also how chemicals get delivered. Like say the blood delivers a hormone and the hormone goes in outside the blood and activates cells. Well, that's how it would happen. Body systems work together to keep these substances in a range of normal. Yeah, that's solid. But it's saying they work together to maintain homeostasis. All right, so the nervous and the endocrine system coordinate other organ systems, just like we said before. They may work differently, but they have the same function. They let the different systems talk to each other, get ready, and work together. It says here, the nervous system is faster, but the effects of the endocrine system last longer. Totally true. If you think about it, the nervous system, we're moving electrical signals, well, electrochemical signals through nerves. They're fast, like electricity. You have a light switch. You turn it off, you turn it on. There's your signal. The endocrine system, it's a little different. Think two ways of sending a signal. One, people are watching. You're going to send Morse code to a message to someone. And one method, you're flipping the lights in a room on and off, on, off, dot, dot, dash, which would be long, short, long. Those signals are fast. That's your nervous system. Instead, you send your signal to the other person. You're going in the backyard, lighting up a charcoal grill, a lot of smoke, got a blanket and a friend who helps you, and you send smoke signals. 3, 4 little puffs, one big puff. Well, guess what? Smoke signals are caused by chemicals that are going to linger in the air for a while. And they're going to be there for a while. You can see them a lot longer. Well, that's your endocrine system. All right. So the endocrine system makes little clouds of hormones that travel through the blood. That's your longer lasting. So it takes longer to send a signal through the endocrine system, but the effects last longer. Nervous system's very fast, on off, but the effects don't last unless you keep sending the signal. Anyway, moving on. So here is the overall of all the body systems we've been talking about. You remember the 2 PowerPoints we had? Come on. Here and here. Those 2 PowerPoints, we're just summarizing it here. It's a good philosophy. Basically, you tell the book, it told you what it's going to talk about, talked about them, and then it tells you what it told you, just to remind you. I'll tell you those 3 slides, the 2 before and the 2 before and the one here, good, easy to pull questions from. I would pay attention to those slides. All right. Oh, and here now we're going to talk about positive and negative. Negative feedback is the primary mechanism, the main one that's used. You need 2 things. You need a sensor and a control center. And so the system can be turned off or on. And that's how a furnace works. That's how temperature is regulated. Example we already used. So homeostasis, they have it at the bottom here, is trying to maintain a balance. So you have a stimulus, say it's, oh, it's too hot, and then you have a sensor that responds to the heat. It's like, oh, we got to do a thing to get rid of the heat. And then the control center is like, ah, we need to, say, sweat. And then you do that and it cools the body. After that, oh, it's too cool. It's too cool. Stop. We got to maintain homeostasis. We can't tip it all the way this way or all the way that way. We've got to try to keep it in the middle. All right. So that's a generic drawing. The next page has how that would work in a thermostat on a house, not in a human. But it shows that if things are too hot, you go through this upper loop of things to have happen, and that would cool the body off. But when the body starts to get too cool, then you're going to go through this lower level, this circle down below, and do things to heat the temperature up. Anyway, you got the idea. And once you have the idea on how to do it with your house, then you can look and see how it works doing it inside your body. So, all right, mechanisms for homeostasis continued. Positive feedback brings change in the same direction as the original signal. Remember, negative feedback, the most common one, it tends to be, here's homeostasis and we're a little high or a little low, or a little high or a little low. We're always wavering around that one thing. Positive feedback, we're here, and then something happens, we push more, and then we push more, and push more, push more. You're going in the same direction the whole time. So, example, childbirth, when the fetus's head pushes on the cervix, that stimulates signals sent to the brain. The brain makes oxytocin, which causes contractions to get stronger, which those stronger contractions cause more oxytocin, and that continues until you have birth. All right. If you had positive feedback and a fever, you're going to cook yourself to death. So, All right, here's a progress check. It's real simple. There are only 2 questions. I will leave you to it for a moment, and then I will continue. So go ahead and mute your computers and discuss. I'm back. All right, let's continue. Oh, wow, was that, how close were we to the end? Oh my, that's the end. That's it for this chapter. All right, I hope that these 2 videos have been helpful to you guys. Go ahead and look over them often and get ready for us to do chapter 5. Everybody take care, and I'll try to have one of these videos ready for you for next week too.